you avoid plagiarism, how you work with scientific papers, how you manage to write a good essay, how you should organize your presentation and your talk. Okay, so, but before I'll do that, I'll give you a brief introduction to why we look at this post-quantum cryptography and what this actually means. So here's the introduction, and the motivation for the seminar goes back exactly 27 years to the year 1994, when Peter Shor, this guy here, showed that there is a polynomial time algorithm to factor integers or to compute the order of elements in finite abelian groups. For example, the groups of residue classes mod P are the subgroups of points on elliptic curves here. Actually, basically, this is Shor's algorithm here. You don't need to understand it. In fact, what you see here is a much more general algorithm. It's called amplification computation of Shor's in finite groups or states in finite groups. So why is this theorem so important for cryptography? It's important because all currently used cryptographic systems, which are the backbone, the foundation of most of today's security technique, rely on things like RSA, DSA, or Al-Jamal. And all these crypto systems can be broken efficiently using Peter Shor's algorithm. So once you can build quantum computers of sufficient size, most of our currently used infrastructure, IT infrastructure, is insecure. In particular, that includes online banking for every single bank in the world. They all use versions of this. Luckily, today's physicists and engineers are still not able to compute or to build quantum computers of sufficient size. This would probably require quantum computers having 5,000 to 10,000 so-called quantum registers or qubits or registers that can store qubits. Currently, the largest quantum computers that people can actually build have about 50 to 70 qubits. So we are still far away to actually realize these quantum computers, but there are several physical realizations that people are looking at. And some people still doubt that they will ever be built, but most physicists probably today think that in the not too distant future, but also not too near future, quantum algorithms of sufficient size to break all these cryptographic primitives can be built. Hence, there is a real need to develop crypto systems that remain secure even if quantum computers can be built, given the current scientific knowledge. So we want to have systems that, given our current knowledge about what quantum algorithms, quantum computers can achieve, will still be secure against quantum computers. And that is what we call post-quantum cryptography. And the main point here is that in post-quantum cryptography, We want systems that can be run on standard classical computers. Computers that only exploit effects of classical physics, Newtonian physics, Maxwell physics, stuff like that, but not what quantum computers makes seemingly so powerful, which are the effects of quantum mechanics. But the systems we want to build use only classical stuff, classical effects, but still are secure against quantum computers. There are also several cryptographic primitives that use actually quantum effects, quantum mechanical effects. That's in particular true for the so-called key distribution, where you can do things exploiting quantum mechanical effects that you can provably not achieve using classical physics. So what we want to do is we want to, in the seminar, look at candidates that, given our current knowledge, remain secure even if quantum computers can be built. And one of the most promising candidates for this stuff of post-quantum cryptography are so-called lattice-based cryptography. In fact, it's the prime candidate currently for post-quantum secure things. Just to tell you a little bit more about this, so quantum computers in particular seem to be a threat to so-called public key cryptography. This is where RSA, DSL, and Al-Jamal are. Private key cryptography, the advanced encryption standard, the stuff that you see when you look at, for example, your wireless router, you usually see it's secured by AES, WPA, WPA2, something like that. Those techniques don't seem to be as much affected by quantum computers as public key cryptography. The reason is that public key cryptography uses more number theoretic stuff. The systems, the primitives, have a much richer mathematical structure that you can exploit using quantum computers, whereas private key cryptography, the primitives in that domain don't use as much mathematical structure. Okay, so, and hence, because this is true, a second line of post-quantum cryptography builds public key primitives from private key primitives, basically. There are also other primitives besides lattices that can also seem to be able to lead to post-quantum cryptography, but in our seminar, we focus on lattice-based post-quantum cryptography. Lattices are also objects from number theory, more precisely from the often called the geometry of numbers. So it combines geometry and number theory in a very nice way, in a very elegant way. And it goes back, as a lot of in mathematics, it goes back actually to Gauss, who did it for the two-dimensional case, but for the cases we are interested in, it goes back to Hermann Minkowski in the late 19th century, who used it to solve famous problems in the so-called algebraic number theory. Okay, but in addition to being post-quantum secure, lattice-based crypto has many more advantages. Lattice-based crypto offers often algorithmic simplicity, efficiency, and parallelism. You can parallelize things. They are often, not always, simpler than other constructions. You have to pay a price. The mathematics behind it is often a little bit more complicated. But once you understand and if you want something really efficient, you have to dig even deeper into the math. But then you get pretty efficient stuff. Another advantage is, and that's again, that really is something that makes lattices unique. We have security from worst case assumption. What does that mean? Security for crypto systems means that with high probability, you should not be able to break a crypto system, right? If you send over your bank account information over the internet, you don't want that anybody can read it. And you want that almost always to be true. If in half of the cases people will be able to read your and listen to your information, you will not be very happy, right? So what we need there is that we need things that cannot be broken with high probability, or even with very small probability. Breaking such a crypto system should almost be impossible. Although looking at the stuff of public key cryptography, how it's designed, there is always a little probability that it's going to be broken, but it should be very, very small. And but in complexity theory, we usually look at worst case stuff, and we much better understand worst case stuff. You know that maybe from NP completeness, which says, so SAT, satisfiability, is NP complete, which means that solving SAT, finding satisfying Boolean assignments to a Boolean formula, is hard in various cases. It's not hard in all cases. It could even be easy in a pretty significant fraction of cases, but there are cases where it's hard. That's not what we need for cryptography. We need something that says, well, this is almost always impossible. And lattice-based cryptography tells us that we build crypto systems that can almost never be broken, unless with very tiny probability, if certain problems are hard in the worst case. So there are cases where these things are difficult. And then you turn that into something that's difficult almost always. And that's not an easy thing to do. In fact, the first guarantees of this type came even later than Shor's theorem, that was in 1997, 1998, where Miklos Aitai was the first to construct such worst case to average case reductions, as we usually call them. And he used lattices, and since then no other examples have been found. Thirdly, lattice-based cryptography is extremely versatile. The holy grail of modern cryptography is homomorphic encryption. You can compute on encrypted data without ever decrypting the data. The result is encrypted, and the guy that does the computation has no clue what he's doing and on what type of data he's doing it. Well, he knows what he's doing, but he has no clue what he's doing, what the result is, but he computes the right, correct result, but computes it in an encrypted form. The only way today to realize homomorphic encryption is using lattices, lattice-based cryptography. In fact, the stuff that we'll see in this course, the basics that we see in this course, also lead to homomorphic encryption schemes. And this is in this general form, they are the only, lattices are the only structure that can lead to these things. Good. Okay, so that's why lattice-based crypto is one of the most important and interesting lines of research in today's cryptography. Okay, and by the way, so we look at things and what I said is not just a theoretical concern, but the National Institutes of Standards for Standards and Technology of the United States started a standardization process for post-quantum secure primitives, namely encryption schemes and signatures, roughly 3 years ago. And they are now into it's a selection process that runs in rounds. And we are now in the 3rd round, and more than half of the candidates still alive, well, actually, I would say roughly 2/3 of the candidates are lattice-based constructions, or things that are very much related to lattice-based stuff. The other thing is where lattices, you can replace lattices, or another area where you can achieve, hopefully, these things is based on coding theory, the theory of error-correcting codes. These things have many things in common, but there are also significant differences. In particular, this stuff here is not known for coding theory-based stuff, and also homomorphic encryption is not known to be realizable using coding theory. Okay, so how do we organize the course? Because this is probably new to most of you, and to help you understand the research papers that form the core of this course, I will give in the next 6 weeks an overview of lattice-based cryptography. I will cover basic definitions and techniques. These lectures are voluntary. You don't have to attend them. There will be no exam or anything like that, but they should, it's my hope that I will be able to help you with the papers that you give. It's based on an overview, basically on an overview paper by Chris Peikert, one of the leading researchers in this area. But I will try to give you some background information, some examples that you will not find in Chris Peikert's notes. But on the webpage, you also find a hint or a link to Chris Peikert's note while you see how he's dealing with this stuff. Then, of course, the seminar topics that you can already see on the webpage for the seminar, they can be selected after a couple of weeks. You can then select preferences in Panda. And then your work or your contribution to the seminar consists of talks of 40 to 60 minutes and an essay of 12 to 15 pages. So to help, these should help you. Obviously, every one of you will get a supervisor for his topic, so that you can always contact and see what kind of stuff you should cover. Usually the papers are much too long to cover in a 45-minute talk or cover in a 15-page essay, so you have to do a selection. We will help you with that. And also we offer hangouts for questions and discussion with, between students and supervisors. And those will be online. Okay. And these will start with the hangouts already next week, I think. Okay, and here are the interesting dates. So starting next week, I'll start with the 6-week mini course on lattice-based cryptography. We'll also cover the basics of crypto, like what's an encryption scheme, what's a signature scheme, what are the security concepts for these things. But in the talks, we'll cover more advanced stuff. We'll cover things like identity-based encryption. We look at things in the so-called standard model and in the random oracle model. We look at zero-knowledge proofs or zero-knowledge protocols. We look at attribute-based encryption. We'll not look at homomorphic encryption. We may look at homomorphic signatures. So then on October 21st or until October 24th, sorry, you can select your preferred topics. The distribution of topics will be done on October 25th. So if there are too many people, well, we have to distribute things, obviously, right? And then until October 13th, you should contact your advisor for each topic. There will be an advisor, mostly me and Lawrence, I guess. We'll deal with that. And then we'll help you with this stuff. Then until December the 12th, you should send us a first draft of your essay. On January 18th, we'll have the presentations, maybe 18th, 19th, depending on how many presentations we'll actually have at the end. And until February the 20th, you have to send in the final version of your essay. Before the presentations, you can also send us drafts of your slides, of what you want to present. But I will tell you a little bit about the slides in a couple of minutes. The Hangouts, as I said, again, voluntary, every Tuesday and Wednesday from 4 to 5 in the afternoon. Use these Hangouts, contact your advisor, ask questions. That will help you a lot. Lattice-based cryptography requires math. There's no way around this. There's no way around, in public cryptography, there's no way around a certain amount of math. And here, it's a little bit more than if you just look at RSA, for example. But you don't need to know anything about quantum computers. Nothing about quantum mechanics, nothing about why these things should be considered secure or stuff like that, or how a quantum algorithm works. So that is not necessary. I will, in the lectures, I will try to explain why we hope that lattice-based cryptography is post-quantum secure. What the difference is, for example, to RSA. Okay, and that's actually quite easy to explain. Okay, so that's the outline for the seminar. The slides will be on the web page as well. We will also stream the video, and you can look at it again. Okay, any questions so far?
Yes, so in the chat there's a question: can short algorithm be used to break elliptical?
Yes. Simple answer is yes. Short's algorithm can be used to compute orders of elements in finite abelian groups, period. And that, actually, it's a period finding. And it doesn't really matter what kind of finite abelian group that is. The only thing you need to be able to do is you need the arithmetic in that group needs to be efficient, but that you need for using it for crypto systems anyway. So, yeah. Any other questions? Yes?
What exactly is the first draft of the essay for you?
First draft of the essay is, this is the stuff I want to cover. This is the overall structure of how I want to present it. We want to see in that first draft that it makes sense, that it is something that's it's not necessarily self-contained, but it's not just taking random parts out of the paper that are not connected at all. But you made an effort to, given the selection that you did, to find something that's sort of well-rounded. Okay, but you don't have to already explain all the details. So I don't want to see proofs necessarily. But I do want to see, look, I want to do this theorem, and I will explain the proof of this theorem in more detail. Whereas for this and this lemma, I will maybe just sketch it or just even do not cover it at all, the proof. Okay? Something like that. Okay.
Another question is, are there any prerequisites for the seminar?
Formally, no. You shouldn't be afraid of math. And in particular, you should not be afraid of linear algebra, and you should not be afraid of probability theory. And we'll need probability theory in this course much more than you usually use it in cryptography. We use Gaussian distributions, special types of Gaussian distributions. We use so-called discretized Gaussian distributions, without which I will explain in the lectures. But we will see two basic techniques to construct lattice-based crypto systems. One is based on the so-called short integer solution problem. It's kind of linear algebra over the integers, which is no longer linear algebra. It's module theory, but never mind. So that's kind of basic. But the other thing that we use is based on the so-called learning with errors problem. And there we use things where we kind of, we introduce noise. Like if you have noise, if you have a connection, a noisy connection, right? And we'll use sort of, you may have heard the term white noise, which engineers usually use to denote some Gaussian independent noise. We'll use Gaussian independent noise artificially to design secure crypto systems. But since we cannot work over the real numbers in cryptography, we'll usually work over something that's discrete, which are lattices. We'll need very special Gaussian distributions. If you're afraid of Gaussian distributions, that's a problem. As it turns out, that learning with errors is a much more powerful problem or technique than just SIS, the short integer solution problem. But sometimes we actually use a combination of the two, depends. But learning with errors is a real powerful thing here. Okay. Any more questions? Okay, maybe I just go back to, because here I said this is the polynomial time algorithm. What's the current status in classical algorithms for factoring? It's much worse. It's the best known classical algorithm is a so-called number field sieve. You don't want to see necessarily what the running time is, but it's much, much worse. And I still think there are just 3 or 4 implementations of it around. So it's a rather complicated algorithm. And it can be used to factor integers of, say, few hundred digits, 200 or 300, but it cannot be used to factor the integers that we used in today's versions of RSA, which tend to have 1,000 or even more digits. Okay? So we are using huge numbers. Okay, any more questions about this? I think next week I'll give you already a sort of a decent impression of the the sort of linear algebra type of things that we use. The probability stuff, that will take a few more weeks. Like in week 3 or 4, I probably start with that stuff. Okay. But so the good news is, so the bad news is, and I know that many students, Gaussian distribution, normal distribution is not something that they like to hear. The good news is we really just need the very basic Gaussian distributions in our course, at least. It's not something really fancy. Okay, any more questions? If not, then I'll give you, as I said, a brief overview of how to seminar. As I said, there is a longer version of this as a video with more examples and more advice that you can find on the webpage. Okay. So, technical hints and resources. So software, we usually prefer LaTeX. In fact, for your essay, if you want to do that in Word, don't do it. Don't make yourself suffer more than necessary. You just cannot do that in Word. Well, you can, but it looks ugly, and it really is a pain. So that's even true for. Well, no, it's not necessarily true for the essay, for the slides. You can do that with PowerPoint or whatever. That's doable, but for the essay, forget it. As I said, presentation software, there's LaTeX Beamer, PowerPoint or Keynote or OpenOffice or whatever should be okay. Okay. But for the technical essays, that's not an option, actually. Templates can be found on our websites for all these things. Where, if you know LaTeX, where we already have environments defined, you have a nice layout and stuff like that. Okay. The next thing is we have links to the papers, the primary sources for your talks on the web page, but you will probably need links to other papers as well, just to look up things, to see what they were talking about, what predecessors of these results there were. And then the question arises how to find that, or how to find in general information that you don't have, that you need to understand your articles. So for example, if you don't know a concept X mentioned in your paper, you can use Google and Wikipedia. It's good for basic knowledge. It's usually bad for more advanced research. And it's not something that you are allowed to cite. Your essays are supposed to meet the standards of scientific papers. And in scientific papers in this area, there are few exceptions, but usually you don't use Wikipedia. And you certainly don't use Wikipedia to say, look, I'm using the following definition of concept such and such. Then you don't cite Wikipedia. You cite a textbook, or you cite an article that appeared in a peer-reviewed journal or conference. That's what you use. But as a first step, I'll use it all the time. Okay? But I also use it carefully, knowing that here, as in all other things that I've written down or that appear on the internet are not necessarily correct. Okay, so always with a grain of salt. Okay. So looking for peer-reviewed papers that you want to read or cite, Google Scholar is a good thing to do. There you find most of the stuff you also find references to other papers. That's very useful to use. There are these archives, archive.org or ePrint at IACR, the International Association of Cryptographic Research, where you find the technical papers. And you can also use entries if you want to use a bibliography. You can use the BibTeX entries, something from LaTeX, from Google Scholar or dblp.org. That's another site where you can find all kinds of links to papers. Okay. Google Scholar is general, DBLP is mostly computer science. Okay. So this is how you find papers and information. How do you work with the sources? So first of all, let me tell you that before I come to plagiarism, if you don't understand a concept that's key to your paper, then you look it up in a textbook, say, and it appears on page 312 in the textbook. You don't start at page 1 and try to make it through to page 312. You probably will fail. What you do is you look at page 312, see, can I understand it? If not, then I see, what do I need from the previous stuff in the book to understand, and then you work your way backwards. You don't read the whole book. I don't know. I maybe read once in my life a math book completely. And I never read a computer science book, at least not, say, contiguously, right? There are some books that over the years I have looked at every single part of it, but I didn't read it in the normal sense of reading a book, okay? And you shouldn't do that, okay? Good, but then, and of course, an important thing is what's plagiarism. What are you allowed? Should you write your essay? How do you cite stuff, things like that. And in the video, you see many examples of what you shouldn't do and how you should do better. But to make it brief, to steal or pass off the ideas or words of another as one's own, that's a plagiarism. That is usually in the humanities and the social sciences. It's much more difficult than in computer science or in the technical sciences. Here in our area, we usually don't put quotation marks around things. Typical thing, you state a theorem that was proven in a different paper. You don't put quotation marks around it. You just say, this is proven in this paper, and I state it exactly as it is stated there. Okay, that's not plagiarism. That's good science. That's the way you should do it. Okay. But then there are, if you copy complete paragraphs from another paper, that's bad. Even if just because you replaced a Greek letter by a Latin letter, that's not okay. Okay. So how do you write a good essay? How do you make sure that you don't just repeat the words, that you just, there are the statements, there are the proofs, there are the explanation of the main ideas. How do you make sure that you do it in your own words? Okay. And there's an easy 4-step process to do that. You understand the paper. That's a good first step. You understand the paper. You outline your essay. This is what I want to cover. And then you put the paper away. And then you write the essay. Okay? Put it to a side and say, look, now I have to do it myself. This seems like a sequential process. In fact, it's not a sequential process. Once you come to this step, you will find that there's something missing here. That's my experience. Right? So if I If I write something down for the first time in my own words, in my own terminology, I often realize, this is something I didn't really think about, and I don't really understand it. So I try to dig deeper. Yeah? Also, sometimes you realize, well, this is something that this step from this line to this line, I thought I understood it, but in fact, something seems to be missing here. Sometimes you think about what's missing for 2 days and realize, there's really nothing missing. I just didn't really understand it, or I just missed something. But sometimes you also realize, look, there could be some more information to go from this line to the next line. And then it's a good idea to include that into your essay. But as I said, it's happened to me numerous times, countless times. I think about for 2 days before I realized there was nothing to think about. Okay. In fact, the problem was starting to think about it, just making it more difficult than it turned out to be. But then, you understand it, you outline it, you put the paper aside, and then you try to write it yourself. That's true also for proof. If you have understood a proof, you should be able to write it down yourself. And then there is no danger of actually repeating things or just copying things. So here it is, what you do. Explain the paper to your reader and explain the paper to yourself. Okay. A good way to do this is go for a walk. Think about a proof. Take a shower. Think about the proof. Whenever I try to prove something new, like I only trust my proof if it survived a longer walk and a shower and a breakfast and probably dinner. Then I kind of get suspicious that maybe I was correct, okay, that the proof really holds up. So this is something, think about stuff. Okay, so that's how you approach the big pictures. Other ways to improve your paper: better explanations, better proofs, more complete proofs. Simplify. Sometimes you say, look, I'm not going to write this down in the complete generality. I try to focus on one case that's simpler, but that captures the basic ideas. And then there is more technical stuff to make it more general. But the technical stuff is really just that, technical stuff. Okay. By the way, formulas are not just random collections of funny-looking symbols. They have a meaning. And if you look at a formula, understand the meaning, right? Not just try to memorize look, there is a Greek letter, then there's an Arabic letter, a Latin letter, and then there were numbers and other funny-looking symbols mixed up, okay? Formulas have a meaning, okay? You should try to understand that. Related work and give examples. Those are other ways to improve the paper. The presentation, there is a difference between the essay and the presentation. The essay must include technical details. The essay, not so much. The presentation, not so much. The essay, technical details, the presentation, not so much. In the presentation, try to convey the main ideas without getting rid of all kinds of information. Okay? It should be informative, but not necessarily that you say, look, I'm in my presentation, here's a result, here's a proof. And then you have the proof on 20 slides. I won't enjoy it, you won't enjoy it, but probably more important for you is that I won't enjoy it. Okay? And you should show that you understand your topic well. guidelines from experience for slides. The rule of thumb is 2 minutes per slide. That is really an average. There will be slides where you spend just 30 minutes. There will be slides where you spend 3 or 4 minutes. Don't overload slides. That's a good thing if you use LaTeX Beamer. It helps you not to overload things because, well, to some extent. But it really does help you. Don't ever use 12 point on a slide. That doesn't work. Okay. You talk about something for more than 10 seconds, but don't have anything about it on a slide. Put something on a slide. Okay. Slides should be the following. You always think about somebody who falls asleep for a few seconds. He wakes up again. Then you should be able to look at the slide and get a rough idea of where you are. Okay. More material than presentations time. Talk only about parts of simplifications, but explain these well. Don't rush through everything. It's fine. It's okay. It's even good if you say, look, for my presentation, I concentrate on this part, or on this line of argument or of development in the paper. That's perfect. Don't do a case distinction with 12 cases in a talk. You may do that later on when you present really interesting scientific stuff for a broader audience for 2 or 3 hours. Then people want to know the details. They expect you to do that, but not here. Talking, practice. Know what you want to say on each slide. The slides are not for you to read. It's for the audience. Okay? Talk to the audience, not to your slides. Okay? It's absolutely fine if you every once in a while forgot what's on the next slide. That happens. It's fine if you have notes. Okay? In fact, I would encourage you to have notes for your talk. Not like where you just read it off, but here I want to say that. Okay? I do that all the time, and I give these talks for several decades now. And I always do that. Right? I may not use them, but I have them ready. Okay? In fact, once you write it down, it's much easier to see how your talk unfolds, what you want to say, where there may be pitfalls, where there may be holes in it, stuff like that. Have an obvious structure. For each slide, what are you talking about? How does it relate to what you have talked about before? What do you want to explain on a slide? What we have just talked about? What's the punchline? A one-sentence summary, something like that. And that's it. So it's all very simple. It's really just a few rules. If you follow these rules, things is much easier. Things will become much easier for you. And as I said, there is a much longer version of this on the web page where you can actually find examples for citations. Also how you should put things on slides. Usually you don't just copy things from your essay on the slide. On the slides, you usually don't have complete sentences. Right? You just abbreviate stuff. In an essay, it would be nice if it's grammatically correct English. Okay? It helps us understand this stuff. Sometimes I just write down, this is just not English. I don't know what you want to say, and that's bad, obviously, right? Okay. And also, just ask us questions about this stuff as well. Not just about the content, but also about this stuff as well. The seminar, see it as one step to writing a master thesis. getting used to the requirements of a master thesis, of an essay that you write, of scientific texts. Okay, questions? If not, then that's it for today. Thanks for your attention, and the first tutorial will be next Tuesday at 2. Same room, and then we'll put the slides for all the tutorials on the webpage. There will be a stream on it. The videos will be there, but it's easier to ask questions if you are here. Okay, good. And that's it. Thanks.